Now looking at just a couple of functions here. So let's look at x cubed and x squared minus 4, and we're going to look at their graphs. So their graphs look like this. This is something we already know. Now analyzing their tangents. Let's start off with the x squared minus 4. The tangents on this side are negative, this negative slope, negative slope, negative slope, 0, positive, 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 and they keep increasing, right? So the slopes are negative on this side, 0 there, and then positive on this side. So if you're going to graph the slope of the tangent function, which is the derivative, it's just going to look like this. The slopes of the tangents are negative here, then 0, negative, then 0, then positive, and getting bigger. Okay? Plus the derivative of x squared minus 4 is 2x. So we can graph that. The derivative of this, well, the slopes of these tangents is constant. It stays as 2. Graphing this line, y equals 2x. The slope of any tangent along here is 2. It's constant and would give you this. That's the second derivative. Let's look at x cubed. So at x cubed, the slope of the tangents here are positive, positive, 0, positive, positive. But the slopes of the tangents are decreasing here. So whenever a function is increasing, you'll notice that, so increasing, the y values keep getting bigger as x gets bigger. So as a function is increasing, the slopes of tangents are positive. So whenever a function is increasing, its derivative must be positive. So on here, we've got positive, less positive, 0, positive, positive. So all the slopes of the tangents are positive. So this quadratic makes sense. Okay? The derivative is always positive except for here. Now, the slopes of the tangents here are actually decreasing. And then they're increasing. This is called an inflection point, where it goes from concave down to concave up. The curvature changes from down to up. Okay? And the slopes of the tangents are decreasing, so the slope of the tangent is decreasing, means the derivative of the derivative is negative, like this. And then the derivative of the derivative, the slopes of the tangents, are increasing, must be positive. So at this point here, we have an inflection point because the second derivative is 0, and there's a change in curvature around there. Okay, so looking at these two again, we've got in this function here, the slopes of the tangents are negative, negative. The derivative is negative. Its slope of the tangent there is 0. The derivative is 0. Slope of the tangents are positive. The derivative is positive. Okay. The slopes of the tangents here are negative, say negative 10, negative 5, 0, 5, 10 approximately. So they're actually increasing, which means that since the derivatives, or the slopes of the tangents, are increasing, it means that the derivative of the derivatives, which is the second derivative, must be positive. So it's positive all the time there. In this one, the derivatives are decreasing to that point. So it's positive 10, say, then 5, then 0. So that's decreasing. So because the derivatives are decreasing, then the derivative of the derivative must be negative. A decreasing function, its derivative is negative. Okay? So we got the second derivative is negative here. And then, after this point, after the second derivative is 0, okay, because the second derivative hits a minimum there, so the slope's positive, 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 0, and then positive again. 0 is a minimum. Okay, second derivative is at a minimum there. And then the derivatives are increasing, which means the derivative of the derivatives must be positive. We've got that there. Let's take a look at another one. So we've got, say, t of x equals x cubed minus 9x. We can factor the x out of this one. Okay, so we factor the x out, and we can graph this function. So there's a lot of information in this graph, though it's one we already know how to graph. What we don't know from advanced functions, though, is where the maxes or mins are. Okay, we know that by factoring this, we're going to have a 0 at x equal to 0 from that, -3 from this one, and +3 from this one. Okay, this is called the inflection point. Changes curvature from down to up. It's concave down here. The slopes of the tangents are positive, 0, negative to that point. That is the lowest slope of a tangent right there. And then they start increasing again. So the slopes of the tangents are decreasing, which means the second derivative must be less than 0. Slopes of the tangents are increasing, which means the second derivative must be greater than 0. Okay? Here's where the max and the min are at -√3 and √3, because if we take the derivative of that function, we get 3x squared minus 9. Try to solve when that is 0, and we factor the 3 out, and we get x equal to plus or minus √3. Okay. Now, here is the derivative of this function. So that's the graph of it. At -√3 and √3, it's at a max and at a min. Slopes of the tangents are 0, so the derivative is 0. On this side, slopes of the tangents are positive. Here, slopes of the tangents are negative. It hits a minimum there. The minimum happens to be -9. And then the slopes of the tangents are positive again after that point. Okay? T double primed, second derivative, is 6x. Now we can graph this quadratic, no problem. You could complete the square and all that kind of stuff, but it's already completed for this one. So graphing a quadratic is now very easy, knowing that the derivative gives you a minimum. So you don't have to complete the square anymore, okay, for the more difficult ones. Now, the second derivative I said here was decreasing. The derivative was decreasing. So the second derivative has to be negative, because if a function's decreasing, the derivative is negative. The slopes of the tangents are negative. Okay? And it's at a minimum here, so that's 0. And then the slopes of the tangents of this one are increasing, so the derivative of the derivative is positive. Okay? So we've got these three for that function. Let's do one more here. Okay, so what about this one here? So say we've got h of x equals nice factored form, x minus 5, x plus 1, x plus 3. We expand it out, we get this. Okay, so if it was in this form here, you'd have to factor it to find the zeros. But that shouldn't be too bad. It's a cubic, you should be able to do that. Okay, so here graphing it, we've got -3 and -1 is a 0 from those two factors, and +5. Okay, so x-axis, the y-axis, and we don't know where this inflection point is yet, and we don't know where these maxes and mins are. But if we take the derivative of this and set it to 0, we will find that. Okay, so h prime of x equals this. Set it to 0 to solve. You could try to factor it, probably won't factor, so I'd use the quadratic formula in this one. Okay, use the quadratic formula, and basically that's what you got to plug it into to find these two values. I'll let you find those values. Okay, so that's where there's a min and max of the original function, where the derivative equals 0. The slopes of the tangents here are positive, positive, 0, negative, negative, lowest negative, somewhere out here, and then start increasing again. So they're decreasing here, concave down, the slopes of the tangents. The function is increasing then decreasing, but the slopes of the tangents are always decreasing to that point. So the derivative of the slope of the tangents, meaning the second derivative, is going to be negative. Here, the derivative of the slope of the tangents is going to be positive because it's increasing. Okay. How do we get this vertex? You could complete the square, like I said earlier. However, that would be silly now knowing calculus. knowing calculus, to find where a minimum is for a function, take the derivative and set it to 0. So if you took this function here, find the derivative, which is going to give you 6x minus 2, set it to 0, and you get x equal to 1/3. Okay? That gives you where this is a minimum, where the slopes of the tangents are a minimum, which is an inflection point. Okay? So it's an inflection point there. And the slopes of the tangents are, for this function, they're decreasing in here. So the second derivative is negative, and then increasing on the other side, so the second derivative is positive. Okay, so back to the first function that we had. First function that we had was this ugly function. Okay, so this nice function here is, we said it was some rational function. I gave an equation for a possible oblique asymptote here, so it could be 5x plus 2. We have an inflection point here. Its concavity is upwards, slopes of the tangents are increasing, then decreasing all the way in here. Okay, so we know that that's an inflection point. That's a maximum. Okay, that's a maximum. That's a minimum. And then we have another inflection point here where the concavity is changing, and another one there. So what might this graph look like of the derivatives? Well, this is what I've got for you. Okay, slopes of the tangents here. So the slopes of the tangents are reaching a constant here. If they're following this oblique line, then the slopes of the tangents are becoming very close to 5. Okay, so we have a horizontal asymptote here for the slope of the tangents. They're increasing to a point where this is a maximum for the slopes of the tangents around here. So right at that inflection point, okay, sorry, I had that on the camera. So the slopes of the tangents here are increasing to a maximum right there. And then so that means the slopes of the tangents are a maximum here. Okay, and then we have a maximum here, so the derivative must be 0, so it must come down through there. And then the slopes of the tangents keep getting lower and lower and lower on that side of that asymptote, so they keep going down like this. Okay, on this side of this asymptote, the slopes of the tangents are really high, and then they go to 0 right at that point. Okay, and they keep going, so they're decreasing here until they hit a minimum right at this point here, that inflection point. Then the slopes of the tangent start increasing again. Okay, until we hit this point here and beyond. Okay, so at this point here, the slopes of the tangents are a maximum for this function, and so we have a maximum for the derivative. And then they start tapering off to 5 again, so they come back down again. Okay, so that's what the derivative function would look like. The second derivative function, well, we now have to analyze the derivative function. Okay, so this is what the second derivative function would look like. Okay, and I'll let you work through that to figure out why that's true. Okay, looking at the possible inflection points for this one and maxes and mins, you can get the second derivative. Okay, that's it for that one.